want to share the screen if I can. And then I have to get my camera. I hope this thing works. Do any of you have a document camera at all or not? Nobody? I didn't think so. I figured that this is one of those things that's more or less for people that do like YouTube and stuff like this that make videos. They would have a document cam, but I don't think you would. All right, got you all up there, I think. Oh boy, this camera gives me trouble. Give me 1 second. I don't know why this thing does this, but give me a second. I'm going to try to get it up there. For the life of me, I don't know why this thing does this. Oh, let's try that. Yes, it worked. That was my fault. All right. So you want 2.42, design an open-ended shunt stub. Is this the one?
Yes, sir.
All right. This is a pretty straightforward problem.
Yes, sir. I think I got it correctly. I checked it with the solution, but I did it a little differently from the solution.
All right. We'll go through this. This is 2.42. So the first thing it says is design an open-ended shunt stub. So it's going to be in parallel. So they got a load impedance of 70 plus J110 and a 50 ohm load. First thing we have to do is find ZL. And let me just do this. Give me a second. So ZL would be equal to that's 70 plus 1J times 110, right? And we're going to take all that and divide it by 50.
Yeah.
And then you're going to get this. And actually, let me call this ZL. And then after that, you're going to find YL, which is 1 over that. And YL would be this. That's going to be the conjugate point you go to.
Yes.
I'm going through this here. Then after that, the next thing you want to do is move to the 1 circle. So on a what I'm going to do is, what do they say is choose a solution that minimizes the length of the through line. Okay. So if they want the length of the through line, that's the line from the load to the actual point the stub is attached. And let me go to my document camera. So if I take ZL, hold on for 1 second. I'm going to move this over here. 1.4 plus J 2.2. So 1.4, this is 1.1, or this is 1. 1.4 is here. Can y'all, oops, so you can't. 1.4 is here. If you have a Smith chart, y'all see that? And 1.4, and then it's J 2.2. So 2.2 is, that's 2.2 is here. And when I come in, I see that this would be the point where ZL is. Do y'all see that, class? Can y'all see what I've done there?
Sure.
All right. Now, I'm looking for my compass. I wasn't planning to do a Smith chart problem. Hold on. Then I'm going to come and draw a circle. You can do this with me if you want. And go around like this. And then take a straight edge. And next, do this. Here's the center point. I'm going to go shoot a line right through ZL and come out the other side. Now, since we're attaching in shunt, this would be YL. You agree with that, everyone?
Yes, sir.
Hold on for 1 second. All right, now the first point, they want the line, the through line to be short. So I'm reading this point here is about 0.448 here, 0.448 lambda. You getting about that, class?
Yes, sir.
If you're doing it, just do it with me. It helps. The more problems you do, the better it is for you. Now, I need to move to the one circle. Well, here's where here's the one circle. When I intersect the one circle, it's right there. So this would be 0.1, this is 0.2, and this would be 0.3. Do you all see that?
Yes, sir.
I'm going to let everybody catch up. Y'all trying this problem at home, people? Go ahead and do it. Believe me, it only helps. The more times you get to do problems, the better. Now I'm going to take my straight edge, and I have a drawing triangle too. I like these. And then shoot a line out there. And now I want to find this point. This is about 0.184. Do y'all see that, class? All right, now when you read this, that's going to be 1 plus J, and if you look, you come up here, it's about 1.9, right? So this point right here is 1 plus J 1.9. Y'all get that, class?
Yes, sir.
Give me a thumbs up if you do, everybody. Just let me, some indication. All right, got to make sure that we're all seeing the same thing. Now, what's my next step? Now that I have that information, I know the length, right? Let's get the length. What do I need to do? This is from the load to where we attach the stub in parallel. I go from the point I landed at, right? The actual length of the through line would be 0.184. Then I subtract 0.448, right? And I add 0.5 to that. And this is all in lambda. Do you all agree with that? Now, what do you get for this? Did you do this, by the way? Whoever.
Yes, sir.
I don't know why I can't see you. You were there a second ago. I don't know why this. Oh, anyway, if you see it, that's good enough. That's the distance. What is this value?
I got 0.237. lambda.
I'll make sure about that. It's probably right. I got it right here. So 0.184 minus 0.448 plus 0.5, 0.236 roughly. So I move this distance 0.236 lambda. That's how far I'm going to move before I attach the shunt stub. Now, what about the stub? It's an open circuit stub, isn't it, class?
Yes, sir.
Just talk your way through this all the time. That way you won't mess up. An open circuit stub has an impedance of infinity, correct? That means when it's normalized, it's still infinite, correct? Now, if I take 1 over that to get to the y domain, I get 0, correct, class?
Yes, sir.
That means the admittance of the stub starts right here. This would be where we start looking. And you'll notice we have to go all the way around a quarter wavelength, right? Y'all see that?
Yes,
Because
sir.
we're getting these values. We're looking for where we get minus j, was it 1 point? Hold on. I need to get minus j. Here it's 1.9, right? So if I look here, I see 1.9 about right here. You can't see that, but right about here is 1.9. Do you all see that? Take a look on your Smith chart. That's minus j 1.9, correct? Now you need to take this and shoot a line from the center of that circle right through that point. And then take a look here on the edge, and that's 0.327, something like that, 0.327 lambda. You getting about that, class?
Yes, sir.
And again, this is going to vary somewhat depending on, you know, how sharp your drawing instruments are and how clear your eyes can see. So now, if you look on this, that's 0.327. I started at 0, right? So 0.327 minus 0 is 0.327. That means that's the stub length. The stub length, I can put it here. The length of the stub would be equal to 0.327 lambda. With me? Y'all see this, class? Show of hands if you do. Question. What if it was short circuit? How long of a stub would I need? If it was a short circuit stub. Anyone? Just unmute yourself and answer. Well, where do we start with a short circuit stub? We start here if it's an open, right?
Yes, sir.
With a short, where do we start? Here, right?
Yes, sir.
Right at this conjugate, right here. This would be, let me move that thing. I'll show it to you with the cursor. There's where we start if we have a short circuit stub in the admittance domain, right? It's infinite and normalized admittance, right?
Yes, sir.
And we move to here. So basically we take 0.327 and subtract 0.25 from it.
Yes.
And that's how long it would be a short circuit. Now that's in parallel. If it's in series, then we work with ZL. We don't work with YL. Follow me? Everybody? And if we were working with ZL, the shortest point would be to here. We'd move from here, whatever that wave, that mile marker would be, to the one circle, which is unfortunately right about there. And you'd shoot a line, and then you would have to, in the impedance domain, remember, you work with normalized impedances with your stub, not admittances. Everybody clear on that, guys?
Yes, sir.
So with stub tuning, just in a nutshell, elements or stubs can be placed in parallel or series, and the elements can be inductors or capacitors. For stubs, they can be open or shorted stubs. In general, you use shorted stubs, and in general, you use parallel capacitors when you do impedance matching. Almost never do you put a parallel inductor? I can't think of a time it's ever been done. So I'm just throwing that out there from experience. All right, other questions? Anything about the bounce diagrams, the transients at all?
Yes, sir. Could you go over those two homework problems if you don't mind?
Which one, first one you want?
2.43 and then 2.44 builds off of it. It just adds a pulse. So adds another line.
2.43 will do. And I'm assuming you have your books, right? Everybody's got a book, right?
Yes, sir.
So put for 2.43, they say consider figure 2.35. All right, they give you, I'm just going to put these values down. VS of 10. They give a RS, that's a source resistance of 30. You can look at it in your book. They give, now I don't like that R naught. That's actually Z naught, right? Characteristic impedance is equal to 50 ohms. Then they give velocity on the line equal to really 2/3 the speed of light. And they give you an RL of 150. And then they give you an L of 10 centimeters. The length of the line equals 10 centimeters. Now you have all this information in your book, but I'm restating. I wish that thing would autofocus a little quicker. Come on, there you go. With me, everyone? After that, if you want to draw it, you can, but there's no real need to. That would be the source resistance. That's VS, all right? At t equals 0 is when it occurs, isn't it? When the transient occurs?
Yes, sir.
So the switch closes at t equals 0. Then you have your load is, I'll just call it R load here. And you want to figure out the voltage. Where do they want the voltage?
At all three, the beginning, the middle, and the end of the...
All right, we'll do the bounce diagram, then we'll get them all. So for the bounce diagram, before we do this, we have to get some critical things. The first is the time it takes to go down the line. I like capital T for that. He uses a T sub L, a lowercase T sub L. I always use capital T. Well, you always take the length of the line, right, and divide it by the velocity to find the time it takes. Does everybody agree with that part?
Yes, sir.
So the length of the line is 10 centimeters. That's 0.1 meters. And the velocity is 2/3 the speed of light. 2/3 times 3 times 10 to the 8th, right? So that's 0.1 over 2 times 10 to the 8th. And you can think of that as what? That's really 1/2, and then it would be times 10 to the -1 times 10 to the -8. So that's going to be 0.5 times 10 to the -9th. And that's simply what? It's really 1/2 of a nanosecond. Is that right, class?
Yes, sir.
Yes, sir.
That's how long it takes to go down the line. Now, at that point, once we have that, we just need a couple of things. We've got RL is 150. We have Z naught is 50. And we have RS is 30. So we need the reflection coefficient at the load. And that would be simply RL minus Z naught over RL plus Z naught. And that's 150 minus 50 or 100 over 150 plus 50 or 200. So that's 1/2, right? And what's the reflection coefficient at the source end? That would be the source resistance, which would be 30 minus 50 over 30 plus 50. So this right here is minus 20 over 80, and that's minus 1/4, right? Everybody got that? Now,
Yes, sir.
you do the bounce diagram, and you're going to first calculate, I didn't put this down here, the V prime. I like V prime for this. That's the voltage on the line just as the switch is thrown. and that's going to be the source voltage, right? Then it's going to be times the characteristic impedance of the line over the characteristic impedance plus RL. So that's 10 over, and Z naught is 50, over 50 plus 30 or 80, right? And that's going to be the voltage on the line. So this is going to be 5/8 times 10. And what does that come to?
Yes, sir.
Yeah.
I thought it was the characteristic impedance and the source voltage, or the source resistance.
Yes, it is the source. I think I put down, I'm sorry I said that. 30 is the source resistance. My apologies. You with me?
Yes, sir.
It's simple voltage division. And what is this value? What is 5/8 anyway? You should know that. So 6.25 volts. Did you get that?
Yes, sir.
Now, I'm going to flip the page and do the bounce diagram. We've got all the information we need right here to do it. But when you flip the page, when I do this and do a bounce diagram, we know what we end up doing, right? We're going to basically, I'll put another thing down here, and I'm going to do this. Some people can draw this neatly. I can't. And if you have engineering paper, it's probably easier. You guys still use those crosshatched green, like light green tablets? No? You know what I'm talking about when I say engineering paper? It's usually, it's got the lines in the back of the paper, and you use the green, light green sides. And if you use engineering paper, they got all the lines, so you don't need to do anything but the diagonals that I'm doing. Like this, I mean these things. So with a bounce diagram, this is time on this axis, right? And this axis. This is the source end, and this is the load. And now we start right here. We have V prime, right? That's just the voltage. It's coming down. The time it takes to here is T, which is half a nanosecond, correct, class?
Sure.
Then it hits here, then what's coming back? Well, what's coming back is V prime times the reflection coefficient, right?
Yes, sir.
Keeps coming back this way, it hits here. Then what's coming this way, it's going to be V prime times the reflection coefficient of the load, reflection coefficient of the source. I'm just drawing the obvious, right? Hits here, what's coming back this way, it's going to be V prime, reflection coefficient at the load squared times the source. And here, it's going to be V prime, reflection coefficient at the load squared, reflection coefficient at the source squared, and so forth. Now, it depends how far you want to go out in time. But I think this is absolutely apparent if you've tried these problems right now. If we want the voltage at the load, we'll start there. I'm going to start here, and I'm just looking down at when I come to the point where something changes, right? That's initially 0. Does everybody agree with that? I come down. There's the first crossing, and I have two things happening simultaneously. I have an incoming and an outgoing wave, right, or point. So if you were drawing the voltage at the load, you would do this. It would be 0, and then your first time constant, which is really 1/2 of a nanosecond, it would change, and it would become V prime times 1 plus gamma L. Now, I'm just putting that down there. If somebody wants to give me the value, you can. I don't know what that is right off the top of my head.
Professor, can you slide the paper up for us?
Yeah, I will. So what is V prime times gamma L, anyone?
Point 325.
Point what?
Sorry, 3.125.
3.125. Anybody confirm that?
Yes, sir.
Total, that whole thing is actually 9.375, sorry.
Oh, well, it should be, yeah, it should be 1 plus gamma L times 6.25, and that's what again?
9.375.
9.375, and it's going to stay there for how long, class? You all see it's 3t because what happens is, here we are, now how long are you going to wait? 1 time constant, 2 time constants before something changes. Do you all agree with that?
Yes, sir.
Remember, we're going down this axis. The only time we change the value of the voltage at the load is when one of these signals, I mean, in this case, both signals, an incoming and an outgoing signal, are present, right? I'm not saying this is as precise as I'd like, but I hope everybody can understand this from the drawing. So it stays there until I hit 3t, and then the value goes to what? The value right here is going to be v prime, then it's going to be 1 plus gamma L. That was already there, and then I'm going to add to it I'm going to add gamma L gamma S, and then plus gamma L squared times gamma S, right? That's the new value. Do you agree with that? It's the old value plus the 2 others. And what's that value going to be? Anybody?
8.2031.
Okay, 8.2031. And how long is it going to stay there? Class? 5t. Yeah. 5t, right? So that's 5 halves or 2.5 nanoseconds. And then what happens? Then I have to add this to it, right? This and this, the outgoing. Correct, class? Now, how many see this right here? It's a bookkeeping problem more than anything. That would be at the load, right? And he,
down a little bit.
yeah, sorry about that. I'm looking at you over here at the same time. Sometimes I have actually 3 screens. You're on one on my right. I'm looking at one in the middle, and then I have my laptop screen here. So that's sort of my advantage. But you all see that's the voltage at the load, right? Everybody got that? Now, Tyler, you asked this. So if I wanted the voltage at the source, what happens? I'll just put it right underneath here. So if this is voltage at the source in, what happens? Well, what is it initially? Anybody? Y'all can unmute yourself and might as well chime into the discussion. This is like Hollywood Squares to me. I'm looking at a bunch of contestants. What do you think? What is it? Anyone?
6.25.
It's just V prime, right? That's the only thing that happens. As soon as the switch is flipped, it's 6.25, right? And it stays there how long? Well, till 2 time constants, correct? And then what does it go to? This is really V prime. Then I have to add what? I have to add gamma L plus gamma L gamma S times V prime. So really it's going to be, this point is going to be, and I don't know what this is going to be V prime times 1 plus gamma L, right? Plus gamma L gamma S, whatever that value is. Can you give that to me, anyone?
8.594.
Is that right? Y'all confirm that? All right. 8.594.
Yes, sir.
All right, it's going to stay there until what? 4 time constants? And then you're going to add this to it. Do you all see that? Those two, which is going to be gamma L squared, gamma S V prime, and gamma L squared, gamma S squared. Then you're going to add times V prime to that, correct? And you can see it's asymptotically approaching a constant value. By the way, both of these things will converge to the same value as time goes to infinity. The whole transmission line will have the same voltage between the interconductor, between the 2 conductors. It'll be as if the transmission line was a short circuit. Now, do you want me to keep going on this? Because I think we're reaching a point of diminishing returns. Do you all agree?
Yeah, this is fine. If you wouldn't mind going over just one of 2.44, that adds in a pulse, so we have to add in another line. It's this
That's
same diagram, you just need to turn it off.
yeah, it's the same exact thing.
Yes, sir. You just got to turn it off at 0.4 seconds.
0.4?
Right.
All right, well, 0.4 seconds is a lot greater than 0.5 nanoseconds.
I'm sorry, 0.4 nanoseconds, yes.
Oh, okay. Well, all right. See, this right here is half a nanosecond, right? Can you all see it? This would be 1 nanosecond, right? Now, if it's 0.4 nanoseconds, that's right before this point right here. So what you'd have is this. You basically have a wave that's going to start right about here, and I'm going to trace it out like this. This is a messy diagram, but you can see what's going on. Something like this. You follow me, everyone? I'm trying to show you this right here. And what's going to happen is this value will be negated. Now this will be minus V prime here. Now when it hits here, this is going to be, see how this is, this one is gamma L times V prime. Now on this one right here, it'll be minus V prime gamma L. Follow me? It's exactly the same as what was done before, only negated. Everybody got that? Now, here's why I'm saying that. If you wanted the voltage, and I'm going to do it the middle of the line, we haven't done that yet. If I just take this and draw a straight line and say I want the voltage halfway down the line, then here's what happens. I start, I get 0, right? Y'all see this? I keep going. As soon as I hit the first one, it goes up to V prime, right? And it's going to stay there until I hit the minus V prime because I have to add that. Then it goes to 0. Y'all see that, class? Everybody? Right? Because I'm adding this plus this. That's the way you do these things. You always add everything. As you're coming down, you just keep adding everything you cross. So here I hit V prime, right? That's going to be at a quarter nanosecond. Then 0.4 nanoseconds later, it just turns off. And it stays off until this point, right? And then it turns on, and then I have, I'm going to have not, if you look at this, I'm not going to have, that one's already killed off, so I'm only going to have V prime times gamma L here. Do you all see that? Right, the first one's gone, right? I mean, this thing has been destroyed by this when I'm adding them. I have V prime minus V prime. You all see what I'm doing? It goes to 0. There's 0 volts there midway. Then what's the next voltage? It's this. So it's V prime gamma L, right? And it stays that way for a quarter of a nanosecond. Then it goes to 0. Are you with me? Then you keep going down, and you're going to see the next one is going to be this V prime gamma L gamma S, right? Which is a small value. And it stays there until a quarter nanosecond later, and then that one's extinguished. Y'all follow me what I'm doing here? Carlin, can you see this okay? You okay with that? I mean, can you all see what I'm doing here? I'm just making sure y'all see this, right? And you understand it. So what is this one going to look like? It's going to be a lot different from this because it's not that additive mixture. You don't continually add something to what was there because the negative part of the wave cancels the earlier part, right? Class? So
Yes,
here's
sure.
what you end up having. I'm going to try to draw this. You can see that this pen's bleeding through. But here's what you have now. And we're doing it the middle just to see it. Here's T. This is 2T, 3T, 4T, 5T. And this is going to V at L over 2, right in the middle. Well, right here at T over 2, I go up to V prime, right? Goes right up to V prime, whatever it is. Now, if that is let's see, that's 0.5. So it's 0.25 is the point. This would be 0.25 nanoseconds is where it turns on, right, class? And then it turns off what? When I add 0.4 to this. So then I have 0.62 or 65 nanoseconds, right? That would be about here. So it's going to stay on, then it goes off. Agreed? Everybody?
Yes, sir.
Now, that's the middle of the line, right? The wave that caused this part to jump up, if you look at it, now if I wait one time constant, which is right about here, right? That would be 0.25 plus 0.5 would be 0.75. Agreed, everyone? Right here, all of a sudden, now I have to add what? Now this becomes V prime times gamma load, right? That's the reflected wave. And it stays there for a quarter nanosecond, and then it goes to zero. Do you agree? And you're going to keep doing that. And I mean, keep going on. And then the next one is going to be what? V prime gamma L gamma S, right? And it turns on right here. And it's going to be a lot. That's be V prime gamma L gamma S. And it's going to turn off at a quarter nanosecond or 0.4 nanoseconds later. Do you all agree with this, class? Now in his solutions, doesn't he show this?
He does, but he stops early. So that V prime gamma L gamma S is actually negative, and he doesn't show that.
Well, it's because gamma source is negative. All right, this thing would flip if I mean, I'm just showing you the values would be gamma L, gamma S. If gamma S is negative, then it would be negative value.
Right, yes, sir. He seems to stop, at least in the solution, my solution that I saw, he stopped after 2 of the pulses and didn't show anymore.
Ah, that's all right. Y'all understand it, don't you, class? That's the way you do these things. And I'll try to underscore the fact that what you're really doing is after you have your bounce diagram right here, after that's shown, the only thing you're doing is tracing down, and every time you cross a line on one of those bounce diagrams of a pulse, you add that to what you already have at that point. So here I've got V prime, then I add minus V prime, I got 0. Next one I cross is V prime gamma load, I add that on, and then here I subtract that, turn it off, and so forth. And bounce diagrams are not that hard. The one thing you have to do is you have to be careful and meticulous. You can get bored by these things, and then you make stupid mistakes. Did we lose somebody? How many people do we have on here right now? Can somebody tell me?
I think 9.
Plus me, so I mean it's 8.
Or 10 plus you.
We got 10 people?
Plus you.
That's fine. As long as we got everybody. It seems people were dropping off or their screens are going blank. Any other questions about this? We could do them at every point, but I mean, that's the essence of it, isn't it? Okay? All right, now, does that satisfy you, Tyler?
Yes, sir. Thank you. I appreciate that.
All right, now we're going to talk about electrostatics. And what I want to do is tell you that I'm just going to say a couple of things out of his book, and then I'm going to go ahead and write some stuff down here. This is chapter 3. And I got to tell you that there's so much information on electrostatics available to you. I mean, there's huge amounts of things that you can see and do. On the internet, they have tons of information. You can look at this from physics books. You've had it already in physics. You can look at it from electrical engineering. It really doesn't matter your sources. The essence is this. Anytime we have a charge, well, he talks about the coordinate systems. Now, you all know Cartesian coordinates, X, Y, and Z, and what unit vectors are, right? Have you all had cylindrical coordinates? Yes or no? Have you? Yeah. Cylindrical coordinates is what? A radial distance rho usually, an angle measured from the XY plane called phi, and then there's a height z. And then there are spherical coordinates, right? I'll try to make sense of this for you. For now, I'm going to just tell you, most of the stuff you've had already. You've had vectors, right? You've had, you know, a vector has magnitude and direction, correct? Like velocity is a vector, 30 meters per second, AX, something like that. Have you all had vectors, right?
Yes, sir.
Okay. Well, the electric field is a vector quantity. I don't spend time with this, the beginning part of that, because most people understand it. I'll go through the coordinate systems with respect to solving problems. I just don't like doing coordinate systems by themselves for no reason. I say that, let me ask you this, because I need to know this. Have you all had spherical coordinates? You have? Well, I want to mention this. With spherical coordinates, there's something I'm going to say, and I'll try to be clear about this. You're always measuring something from the center of the origin, or 0, 0, 0. That's where X, Y, and Z are 0, to the point of observation. And that distance is called R. I hope you see it in your book. It's on page 127. Then you have two angles in spherical coordinates. You're measuring one angle from the z-axis to the actual, an angle between the z-axis and the radius vector r. I hope you can see this. And that's called theta. If you have your books, you can look in your books on page 127. And then you're measuring a second angle, which is the projection of this vector r onto the horizontal plane. You're taking that first, then you're measuring the angle from the x-axis to that projection. That's called phi. You all see that? Can everybody see what I've got on that screen there, class? Now, how many have had that before? Just a show of hands. 1, 2, 3. Everybody should have had it. If you haven't, somebody cheated you. You should have all had it. Now, here's one thing you may not have had. There are unit vectors associated with this coordinate system. The unit vector AR is in a direction that's in the direction of R. It has a length of 1 and it's straight away. Can you all see that AR, what I try to draw there? Then there's a unit vector A theta. Now, I mean A theta. A theta is going to be tough to see. It's perpendicular with AR, but it's in this direction. It's in a direction that if you start rotating this tip and increasing theta, the way the tip of this vector would move would be in the direction of A theta. Can you all see that, people? How many can see what I'm talking about right here? All right, and there may be a picture on the next page where he shows this, but there may not be. It's a tough one to show. Anyway, that's A theta. Now, go ahead.
A theta is perpendicular to AR?
Yes, all unit vectors are always perpendicular to each other. AR is perpendicular to A theta, is perpendicular to A phi. Now for A phi, I'm going to do it right here. A phi is a unit vector in the direction of that the tip would move if you increase phi. So you can see that it would be in this direction. That would be A phi. It's hard as heck to draw these right here for me. This would be A phi. All three are orthogonal to each other, or perpendicular. And I don't see a drawing in Dr. Wentworth's book where he has these shown. But that's the real thing that you get catches you on, is the unit vectors. You have to understand the direction of them. I have some information I can share with you. I'll send it, or I'll put it on OneNote, okay, that has better depictions of this. Have you had unit vectors before in spherical coordinates class? If you have? You have. All right, good, good, good. I'm very thankful that you have, because the unit vectors can be irritating to get a handle on. And remember this. Now, with Cartesian coordinates, when you had X, Y, and Z, AX is always in the same direction, isn't it? It never varies. It just points in one way, right? But what happens think about this. What happens to AR as I change theta and phi? Well, if I rotate this around here, AR is pointing in a direction that isn't parallel with this direction. You see what I'm saying? Just think about it. AR is in the radial direction, but if it's dependent, it's real directional sense. If you projected this into the X, Y, and Z plane, It depends on the angle theta, right? Doesn't it? What I'm saying is if you take a look at the tip of this thing, right, and let phi increase, well, it's pointing this way here. Well, if you let phi increase by 180 degrees over here, it would be pointing in this direction. It's still AR, but if you project that into the X, Y, Z plane, now it's going to have a different sense. Here, AR has positive X, Y, and Z, doesn't it? Look over here to 180 degrees. Over here, it has negative AY, right? Right? If you just project that vector into the Y, it's negative, correct? Let me try to draw that if you don't understand it. I'm trying to make sure you understand that the absolute vector directions in AX, AY, and AZ never change. They will all, AX will always be in the same direction regardless of angle, regardless of anything like that. But in spherical coordinates, now I'm going to do this. What I'm going to do is this. I'm going to take a 2D like so. Call this the Z-axis. Call this the Y-axis. And let X just be 0. Now, if I have R here, all right, that can be at phi equals 90 degrees if you want to look at the picture in the book. Now, this is my AR, right? And if you want to make this 45 degrees, then I could say that AR right here would have what? It would have a component AY, which would be equal to 1 over the square root of 2 AY. And vertically, it would be 1 over the square root of 2 AZ. So I could say at this point that I'm showing you right there, AR could be depicted as 1 over the square root of 2 AY plus AZ. Can you follow what I'm doing here?
Yes,
I'm
sir.
taking,
Could you
oh, I'm
skip
sorry.
over-
Yeah, I'm sorry. Sorry, I lost it. Here's what I'm trying to show you. If this is AR right here, now I'm getting rid of X altogether. I'm just writing the plane of the paper, let X be 0. And I'm taking a look. If that is AR, that's the radial distance. R, that's AR. And if this is 45 degrees, a unit vector AR at that point would have 1 over square root of 2 AY plus AZ. How many see that right there? Right? Unit vectors have to have a magnitude of 1. That does, right? It's just taking the projections of AR, which has a unit length of 1 in the Y-axis, on the Y-axis, and then on the Z-axis. You all see that? Now, add 180 degrees to the angle phi. Now I come over here, right? And here's my distance R. R still the same. This would be AR here. It would be at an angle of 180 degrees in phi, increasing. Now you can see when I project that vector AR onto the onto the Y and Z axis, AR here would still have a magnitude 1 over square root of 2 times, but it would be minus AY plus AZ. Can you all follow me on that, class? So I'm trying to warn you that with spherical coordinates, the unit vector AR and the unit vectors are functions of the angles that you're at. I mean, in terms of their absolute direction. So you have to be aware of that. You good with that, guys? I know it's a little confusing. I mean, if you're in Cartesian coordinates, AX is always in the same direction. Never changes. AY always in the same, AZ always in the same direction. In spherical coordinates, the vector direction AR is a function of the angle phi. And that's important to know, and theta, to be frank about. Got it, guys? We'll do this. So, having said that, I'll do cylindrical. I'll send you a picture with all the vector coordinate systems and unit vectors associated with them after this lecture today. Yeah. But I wanted to show you a couple things, and then what I like to do with electrostatics is work problems and we'll talk about the theory, but it's better to work problems. So cylindrical coordinates, I'm not going to talk too much about them. I think you've had cylindrical. He talks about cylindrical coordinates in his book. And, cylindrical coordinates have unit vectors too. You've had these unit vectors from the way I think you all have had them, right? I'm just refreshing your memory. with cylindrical coordinates, you have an A phi. The A phi in cylindrical coordinates is the same as the spherical coordinate A phi. But here you have an A rho, and that would be a unit vector that's radially away from the axis, the z-axis. And you also have AZ, and AZ is the same AZ as it is in Cartesian coordinates. Okay? Now, so with that in mind, actually, let me go ahead and start the lecture by, and I'm going to do this the old-fashioned way. I'm going to start with how this stuff, how we came to know this, all this information. So hang on for a second. Now, you've had physics, right? One thing physics tells us, the physicists tell us, that every single thing that we have that is mathematically expressed is based on experimental measurements. There's nothing in physics that came down from Mount Sinai and God said, right? There's none of that. This stuff is based on observation, verifiable, reproducible observations. So when we talk about the electric field force, this is the thing you can actually visibly, you can measure this. You can see a displacement on a spring or something. So if I have two charges, call this Q1 and Q2, charge will be in coulombs, by the way, and we have a distance between them, a distance d, then we can say that the force on either one will be this. It will be something that will be either retractive or repulsive. And let me go through this. Now you've had it, so I'm going to just say this. The force on charge 2 created by charge 1, I'll just call it F2, is equal to Q1 times Q2. And by the way, charge Q is in coulombs. I think everybody knows that, right? You've heard of Coulomb before, right? It's equal to Q1, Q2 over 4 pi epsilon naught. And here, epsilon naught is the permittivity of free space. Now, if it wasn't a vacuum or air, if there was another material, we would multiply this by epsilon relative. But for now, just epsilon naught. And epsilon naught is usually given as 8.854 times 10 to the minus 12 farads, or the way Dr. Wentworth likes to write it is 1 over 36 pi times 10 to the minus 9th farads. Do y'all remember this part of it? Do you remember 1 over 36 pi times 10 to the minus 9th, or you remember 8.854 times 10 to the minus 12? Do y'all remember this constant? You remember this is called the permittivity? How many remember that?
I remember the 8.854.
All right, that's fine. They're the same thing, basically. Well, this is actually more of an approximation. It's that, but then down here, you're going to have the distance between them squared. So, matter of fact, let me change that from D to R and make that a vector. It's actually over R vector squared, and then a unit vector AR. And AR is a vector that points away from the source charge causing the force. So if I wanted the force on 2, AR would be pointing in this direction. That would be AR here. And if I use this force law on Q1, AR would be pointing this way. Does that make sense to everybody? Here's what you gather from this. AR has just got a magnitude of 1. Forces are proportional to the charges. They're direct, increase the charge, increase the force. They're inversely proportional to distance squared. And they are weighted by a constant 1 over 4 pi epsilon naught. Now, the reason I showed you this right here, if you take a look at 4 pi epsilon naught just for a second, if I have 4 pi epsilon naught, what I actually have is what? 4 pi and then divided by 36 pi times 10 to the minus 9th, don't I? That's 4 pi epsilon naught. Correct, class? Y'all seeing this, right? Well, what is that equal to? Isn't that 1 over 9 times 10 to the 9th. 436 is 9, correct? So that's 1 over 9 times 10 to the 9th. That's here, right? In the denominator. If I take that to the numerator, what do I see the force is equal to? It's 9 times 10 to the 9th, Q1, Q2, times AR. Isn't it, class? Now, when you had physics, do y'all remember 9 times 10 to the 9th, that constant that was there when you had force equations? Anybody?
Yes, sir.
All right, that's one that, you know, there's two constants you keep on getting. There's a gravitational constant. Usually they have K there, right? That has to do with mass 1, mass 2 over R squared times K. Do y'all remember that? Then there's the electrostatic constant, 9 times 10 to the 9th, Q1, Q2, and it's divided by R squared, AR. I like that because it's easy to remember. 9 times 10 to the 9th instead of 4 pi epsilon naught. 4 pi epsilon naught, sometimes people get a little finger fatigue and forget to write something. But here, I got that. So that's the force between, if you have two charges, what it is between the charges, right? We could do a problem on this, but I think it's fairly simple and obvious. Now, here's where things kind of get messy. Let's do this problem as a class so everybody sees this. And we're going to do it with vectors. All right, here we're going to have X. I'll just make it two-dimensional, Y. You got to make sure everybody knows this. Now, I'm going to have the first charge located at the origin, Q1. And I'm going to have the second charge, Q2, right here, located at a distance 1, 1 from here. I'm going to let Q1 be equal to Q2, be equal to 1 microcoulomb. Just do this problem with me, it'll help you. And what I want is the force on Q2. So I want F2. I want you to tell me what it is. Now remember, I didn't draw a line connecting them. I just said there's two charges. One is at the origin, one is at the point X and Y equal 1. And there's the coordinate scheme. Z is 0 for all intents. All right. So how do I get the force on Q2? Well, the force on 2 would be Q1, Q2, right? So that's 1 microcoulomb is 10 to the minus 6, right? So it'd be 10 to the minus 6 squared, right? You all with me? Then it's times K. K is 9 times 10 to the 9th. You all agree with that? It's 1 over 4 pi epsilon naught. I just call it K. You all with me on this, class? Then it's times what? AR. I'm going to have to get a unit vector pointing in this direction, divided by R squared. And I'll just put AR and magnitude of R squared. And we're going to get these values now. So when I take a look at the vector associated with point 1 going towards point 2, my vector R right here, and I'm saying it's going from 1 to 2. That's the key thing. That vector is going to be, here's how you get it. You take the coordinates of the point of observation and you subtract the coordinates of the source of the electric field. And you put them in the respective, you have to do this in a way where it's going to be, it's going to be a vector sense to it. Let me explain this. So if you go ahead and look at the point here, this has point X equals 1, Y equals 1, Z is 0. Do you agree with that point in Cartesian coordinates? This has the coordinate 0, 0, 0, correct? With me? Now here's how you get the vector direction R, and I'll do it here. R itself will be equal to, you take the coordinate X that you were going to, X2 minus X1, AX, plus Y2 minus Y1, AY, and if there was a Z, plus A's, or plus z2 minus z1 az. That would be a vector from point 1 to point 2. So if we do it, we get 1 minus 0, don't we? Or 1 ax plus 1 ay, and we would have 0 az. I want you to just take care, make sure you understand it. Do y'all understand what I've done there, class? Give me a thumbs up if you do. That's a vector in the direction from point 1 to point 2 that has a length, an actual length, right? Now, if we wanted a vector from 2 to 1, it would be minus that. Do y'all see that? It would be the same exact coefficients, just negative, correct, class? Because I'd be moving the opposite direction, right? That's AR. If I want a unit vector in the direction of that vector, I simply take R vector, the same one I have here, and divide it by magnitude of R vector. That's a unit vector, and it's given the symbol A sub R in Dr. Wentworth's book. So if you take a look at that, what would a unit vector be, class? Well, 1ax plus 1ai, and what's the magnitude of R? Can someone tell me? How do you get magnitude of anything?
Square root of 2, the Pythagorean theorem.
Right. You would go ahead and you would say the square root of really the x delta x squared plus delta y squared, right? The difference in x, difference in y squared, correct, class? And in this case, and since the difference is this vector r would be 1 squared plus 1 squared is 2, square root of that. So this would be really AR would be 1 over the square root of 2ax plus 1 over the square root of 2ay. Y'all see that? So I'm going to flip the page on mine. Admittedly, it's a little messy, but I hope you appreciate what I'm trying to get at. Let's flip the page together. And then you have this. Now, that force, this is the force on 2, would be equal to Q1, Q2, and that would be 10 to the minus 12th. Do you all agree with that? If it's the charges are 1 microcoulomb, a micro is 10 to the minus 6, so it's 10 to the minus 12 if you multiply them. Then I have to put the constant k, so that's 9 times 10 to the 9th, right? Y'all agree with me? Then I have to put the unit vector, right? And the unit vector was really 1 over the square root of 2, ax plus ay, correct, class? Then I have to divide it by r squared, don't I? And what was r? It was the square root of 2, right? And therefore r squared would be 2. You all agree with that? Take a look at the equation. I want to make sure everybody sees why, what I did and why I did it. Are you all clear on that? That is the fundamental force between two charges if the charges are both 1 microcoulomb and they are both located, one at the origin, the other at point 1, 0. And I did this, and I'm trying to just make sure you all got a feel for the way this works. Now, if you go ahead and knock out the math on this, what do we end up with? Well, you actually get what? F2 would be equal to, I have 1 over 2 square root of 2, right? So that's really 2 to the, what, 3/2 power, isn't it? Right? So I have 1 over 2 to the 3/2 power. Then I have 9 times, well, this 10 to the 12th, 10 to the 9th is 10 to the minus, what? 4, isn't it? Right? Or, sorry, if I have, that's minus 3, right? 10 to the minus 3 here. And then I have just ax plus az, and that would be it. You could do the math on this one. Do you all agree with that, class? You could do the division. But that's how you get the force. Magnitude and direction. It's ax, ay, pardon, right there. Now, the next thing is an extension of this. That's the force on a particle, the force on a charge created by another charge. I want to just mention this. If you have any number of charges, say you have Q1, you have Q2, and you have Q3, and then you have some Q4, and you want the force on Q4 right here. What you end up doing is take the force from each one of these charges. So you would take the force from 3 on 4, from 2 on 4, and from 1 on 4 and add them. You would just say this would be equal to the force caused by Q1 plus the force caused by Q2 plus the force caused by Q3. And these are vectors, so you have to add them vectorially. How many remember seeing that back when you had your physics courses? You all remember this? You add the forces in a linear fashion. And it doesn't matter how many charges you have there. So then the next thing that they do, I'll work problems and I'll extend this. So then they say if you have any type of either line of charge or plane of charge or volume of charge, you can say the force between any other charges and another charge can be written as an integration. But before I do that, and he doesn't do it this way in the book, what we really like to do is not work with forces so much as electric field values. Now here's what happens. If we know that the force on the charge is on, say, charge 2 was Q1 times Q2 AR, say, call it 2, divided by 4 pi epsilon naught magnitude of R squared. Right, this is the general force equation, right? What we do is divide that force by Q2. So this is at point Q2. If we divide it by Q2, we get this. And now we have force in newtons divided by charge in coulombs, and that gives us an electric field. Now I want to focus on this. That would be an electric field, and the units of the electric field are volts per meter. Do you all remember electric field, right? This is the one we're going to focus on, and I'm going to spend most of my time on. I can get the force just by multiplying it by charge Q2. How many remember electric fields, the value for electric field, right? In his book, and I'll show you what he does in his book, but I really want to do some problems with this. What he does is he tries to introduce you to the concept of electric field by saying, if you want the electric field at a charge, you know, the force on a charge is dependent on the charge value, right? But if you divide that charge value out, you get a term that's called the electric field. And that is the thing causing the actual force on the charge. So if you take the E field at any point, here he's calling it point 1, and divide it by the charge there, that you get the electric field at that point. And really what you find is the electric field caused by a single charge. Try to follow me on this part. It's not hard, but just listen to me. What you're really about is if you have a charge and you want the electric field at any point in space, you just take that charge divided by 4 pi epsilon r squared AR. And both AR is a unit vector in the direction. The way the unit vector is found is by going from the source, or where the charge is that's causing the electric field, to the point of observation of the field. That is what R is, and AR is a unit vector in that direction. You remember the electric field, people? It's very similar to the force. You just divide out the second charge. It's the same thing. And he shows you this. Something to give your mind something to work with. When we think about electric fields, they're vectors. We try to think of things, get sort of an image of this in your head. And if you have a charge centered there, and you talk about the electric field around it, it would always be pointing away from the charge, if that's positive charge. And this is in his book. And it will always decrease the further away you go. It decreases as 1 over r squared. So technically, as you become closer and closer and get infinitely close to a charge, the electric field value goes to infinity. Can you all see that? Because you have 1 over r squared, right? How many see that? With me? Now, here's a puzzle for you. Well, here's something to consider. You know the basics of an atom, right? What's in the center of an atom? There are positive charges called what? Protons, and there are neutrons. Do you all remember those? You had to have some of that somewhere in your life. Well, the proton actually has a radius. This gets into to do justice to this, we'd have to actually get into quantum physics. But well, you can see that if you got two positives, suppose the thing has 3 or 4 positive protons. Say, I mean, what helium is 2 positive protons, isn't it, class? And 2 neutrons. That's what helium is. Well, think about that. The protons are right next to each other. What's the force between those? It's enormous, isn't it? Think about that. You can do the math on this. Calculate the charge of 2 protons, then the distance between the protons, the theoretical distance. The force is absurd. So what prevents those 2 protons from just flying apart? It's called a nuclear force. The nuclear force is similar to the electromagnetic force, but it's attractive in nature, and its attractive force power is like 1/r⁶. So the nuclear force is like hooks that hold those things together. Now, this is interesting. And with when you're talking about nuclear fusion, when you actually slice that nuclear hook, there's a threshold, then the electrostatic forces repel the thing, and then you get a nuclear explosion. So what I'm really getting at is the essence of a nuclear explosion, the real thing, is when you cut the hooks that are holding those protons together, and then all heck breaks loose, and you get unbelievable amounts of energy. Keep that in mind. It's not precise, but it's a pretty good rendering of what actually goes on when a nuclear weapon goes off. And you all know what a nuclear weapon is, so I don't need to talk about that. That's what everybody's wondering about these days with some of the I guess, problem children in the world. If they get a hold of one of those, it's going to be a bad, bad day. All right, now I'm over by 2 minutes. I didn't really get to a lot of the lecture. I'm going to give you some homework. I want you to work at it. And I usually give a quiz on Friday. I already gave you a Smith chart quiz. How about we do a quiz on Monday instead of Friday? Because we're just entering this material, okay? I'm going to give you some homework problems, give you some reading to do it. And then is that all right with everybody? On Monday, we'll have the quiz, because we're not going to have enough material to give a just quiz on Friday. And I don't want to give a quiz just to give a quiz. I want to give you some homework, and we'll go over it. And does anybody have any questions before
So will the Monday quiz be on bounce charts or
Theoretically, it could be on anything we cover up to that point, but
right.
it will be probably on chapter 3, electrostatics. All right. I could put a small one on a bounce diagram, just do three bounces or something like that. Give it for 3 time constants. But I'd like you to focus on the electric flux density right now, and really the electric field. Okay. How many had their physics at Auburn? Raise your hands. You had it at Auburn University, physics. How many had it somewhere else? Okay. Where did you have your physics? Caleb?
Southern Union.
And the problem I've had in the past is people that have their physics and calculus taught at community colleges, oftentimes we're not taught certain fundamental things. And so if you have questions, be sure you ask me if you don't understand what I'm doing and why I'm doing it. Because most of the stuff we're going to be covering has been covered thoroughly in the physics, but in your physics courses right now, the beginnings of it. But let me know if you don't. Okay. Anything else for the good of the group?
I have a quick question.
Go ahead.
Last time you said we can search something online about Smith chart to do some, practice. What word should we type in instead? I forgot.
You want problems for Smith charts?
Yeah.
If you just type in and just took homework problems, Smith chart, you're going to see something called Chegg or something like this. It's some kind of a,
Yeah.
You will see a million Smith chart problems probably. If you really want some more, I'll send you some. But there's tons of them out there.
Okay, and it's all kind of related to what we learned.
Yeah, and I'll tell you, matter of fact, here, I'll give you some, I'll just do this. Since this is theoretically my office hour, let's do this. You should have been able to get, well, let's see. Give me 1 second.
Mm-hmm.
There you go. There's a ton of them here.
Okay.
You can't help but run into problems, and I can do this for you. I can literally put this in. I can find it. Chat here. Hopefully,
Okay. Thanks.
y'all see that in chat? There, just copy. If you want Smith chart problems, they're all over the place, and there's not just a few. There's probably a million out there. And I encourage you, go look at other resources, do some problems. They're created by other people. There's so many problems that are available. And that's one thing I really like about being online is that the amount of material that you have available to you now is insane. And you can find lecture material about anything, problems about just about anything, and solutions. If you want to pay for something, you can get probably, the solutions manuals to anything. There's nothing that's hidden out there, frankly. And that's really the smart thing, is just find a bunch of problems and do them. When I was where you are, what I would do, because in our books, we had answers usually to every other problem. They'd put the answer in the back of the book, and there would be cajillions of problems. I used HATE for my undergraduate electromagnetics courses. It's HAYT. It's a great book. And I would do every odd problem, and there would be like 50 to 100 problems in each chapter. And they took me a long time, but I tell you, that burned that stuff in my brain. And if you want good grades, spend a lot of time doing problems. You'll never have problems getting A's. You really won't. If you don't, you'll have a lot of problems, assuming you have the ability. But it's really perseverance and time spent working problems and understanding that pays off if you're in engineering. Because you can take some of the brightest people, and I've seen this, some really bright kids fail out of here because they just wouldn't study and they wouldn't apply themselves. And I've seen some not so bright people, mediocre people like myself, just work their tails off and do very well. And so the amount of time you spend doing the problems, asking questions, it pays off big time. And then you don't forget it either. Come final exam and in your next courses, you'll retain all that. All right. Anything else for the good of the group? Listen, take care. I'll see you Friday. I'm going to give you I'm going to give you some homework, and I'm going to ask you to please do the homework, and we'll discuss it. And if you have questions, send me emails, but make sure in the subject you put like EMAG 1 or ELEC 3310, because I get too much email, and I frankly can overlook one unless I see something like that sticks out at me. Everybody got that? Okay, and don't send me emails from Gmail or Yahoo or anything like that. Make sure it's from your auburn.edu account, because the browser that the email account with the university, they're doing stuff, and they're literally putting all this stuff in the junk if it's got like a Gmail address, and I don't go through my junk folder. A lot of it at least gets put in the junk. Anything else? Because I'm going to go ahead and take care of things. Anything? All right, y'all take care. We'll see you Friday then. Okay.